All right, this is lesson 26, example problem 2. So we have a simply supported beam that has a 500-pound point load as well as a 50 pound per foot distributed load on the right side. It's simply supported with a pin support at A and a roller support at B. All right, so we're asked to solve for the reaction forces and then draw the shear and moment diagrams. All right, so first thing we're going to need to do when we're solving for the reaction forces is we want to come up with an equivalent point load for the distributed 50 pounds per foot load. It is possible to do this problem leaving it as a distributed load, however, it requires you to do some calculus, which I'm sure we're not all super excited to do. So if the load is 50 pounds per foot, and it is 6 feet long, then you know that the total force is 300 pounds. And also, if it is starting at the 6-foot mark, right, it starts halfway across our beam, and it goes all the way to the 12-foot mark, then the force will act at the equivalent point force will act at the center of this distributed force. So if it goes from 6 feet to 12 feet, it'll act at 9 feet right in the middle. So our equivalent beam for doing our statics and reaction forces, we're going to have a vertical AY, we're going to have a horizontal AX, we're going to have a downward 500 pounds, we're going to have a downward 300 pounds, we're going to have an upward, or I guess I've been using B sub y for these, so I'll try to stay consistent. So by, we know that this is 3 feet, this distance is 6 feet, this distance is 3 feet. Therefore, that gives you that whole distance is 9 feet, and the entire thing is 12. All right, so we'll go ahead and get started. Summing the forces in the x direction is equal to 0. The only force in the x direction is ax. Therefore, a sub x equals 0. Sum of the forces in the y direction is equal to 0. We have a positive ay, a negative 500 pounds, a negative 300 pounds, and a positive by. One equation with two unknowns, so we're going to do sum of the moments is equal to sum of distance times force is equal to 0. We're going to sum around point A. So that's going to give us AY times 0 minus 500 pounds. Sorry, I guess I need a positive. Rotation is going to be counterclockwise. So minus 500 pounds times 3 feet minus 300 pounds times 9 feet plus BY times 12 feet. So we solve through for BY, and we get that BY is 350 pounds. If we plug that back in up here, we get that AY is 450 pounds. All right, so now that we have our reaction forces, we can do our shear and moment diagram. So one thing to keep in mind, when you solve for your reaction forces, it's useful to take that distributed load and change it to a point load, or an equivalent point load. However, when you go to do your shear diagram, you have to go back to looking at it as a distributed load. So I'm going to go ahead and, just like in the previous problem, I'm going to draw a little horizontal line, and then I'm going to put all my forces on it. So I have my AY, my 450 pounds, I have my downward 500 pounds, then I have my distributed load, that's 50 pounds per foot. And then all the way on the right side, I have my upward 350 pounds for BY. Okay, so shear diagram. So shear as a function of x, this is all going to be in pounds so that I don't have to keep writing it over and over again. Then we have our x-axis, which is going to be in feet. So we start at 0, 0. And we move left to right, and every time we hit a force, we go up or down. So our first one is a positive 450 pounds. So we're going to go up, to 450. Now we're going to go across because we have no forces, and then we have a downward force of 500 pounds. So we're starting at positive 450. If we go down by 500, we end up at negative 50. So then we have no forces for a while, and then we get to 6 feet at the start of our distributed load. So because we have a negative force, it tells us we're going to start going down. Just like in the previous example, when we integrated to go from a horizontal line to a linear line or linear slope, it's going to be the same kind of thing. So we know we're starting at negative 50 pounds, and we know that the distributed load in total is another negative 300 pounds. So that means when we get all the way to the end of the distributed load, we have to have gone down by another 300 pounds, which means we'll end up at negative 350. And that's at x equals 20. So we know we have to end up at this point down here. So now, for our distributed load, we can go ahead and just connect the dots, draw a nice straight line between them. And then the last force is our upwards, 350, brings us right back to 0. So just like in the previous problem, we started at 0, we ended at 0. We know we're in a pretty good spot. So things we learned from this. 1, you will take your distributed load to an equivalent point load when you're doing your solving for reaction forces. But if you don't take it back to being a distributed load before you do your shear diagram is going to be wrong, right? Because if instead of having that distributed load there, we just had a negative 300 pounds, right? We would have ended up with something where this line stayed flat until all of a sudden it jumped down and then stayed flat again. And that's obviously not what we ended up with when we did it the right way. So that would have been bad. So that's bad. You have to bring it back to being a distributed load. So that's our shear diagram. So next up is our moment diagram. So remember, moment equals the integral of shear. So again, doing our moment by doing solving for area. So our first area, right, our little rectangle here is 3 feet across, 450 pounds tall. Therefore, 3 times 450 gives us 1350 foot-pounds. Okay, so next up, we have another rectangle that's another 3 feet across and negative 50 feet tall. Therefore, that's going to be negative 150 foot-pounds. Okay, so our next area is a little harder because it's a weird kind of shape, but you can break it up into a rectangle plus a triangle. So the rectangle part is going to be base times height. It's 6 feet long, negative 50 pounds tall, gives us negative 300 foot-pounds. The triangle, 1/2 base times height, gives us 1/2 times 6 feet. And then if it starts at negative 50 and goes to negative 350, that means the height is negative 300 foot-pounds, or negative 300 pounds. So negative 300 pounds, right? So do that math, and that gives us negative 900 foot-pounds. Okay, so all in all, the rectangle and the triangle together are negative 1200 foot-pounds. All right, so now that we have all of those ready to go, let's go ahead and label it negative 1200 foot-pounds. We can start drawing our moment diagram. So we have x, which is again in feet. We have our moment, which is in foot-pounds. So we start at 0, and then we have important spots at 3 feet, 6 feet, and 12 feet. So by the time we get to 3 feet, we've gone up by 1,350 foot-pounds. So we know that we go to there. So, boom. So there's our going up. And then we have a spot where we go down by 150 foot-pounds. So 1,350 minus 150 is 1,200. So we have to be at 1,200 by the time we get to 6 feet. So we connect those lines. And then we have our negative 1,200 foot-pound triangle rectangle combination figure, right? So remembering back to calculus, when we did integral of a constant, it gave us a linear shape. When we do integral of a linear shape, you end up with a quadratic, right? Remembering all the way back to Calc 1 and Calc 2. So if the integral of a linear shape is a quadratic, it means we're not going to draw a straight line as we go down by these last 1,200 foot-pounds. We're going to go down in a parabola shape. So draw a nice little parabola shape that's always going down but goes down at an increasing rate. And then since we started at 1,200 at 6 feet, and we go down by 1,200 over the course of that combined rectangle triangle, it tells us we have to get all the way back down to 0 by 12 feet, which checks because our moment diagrams need to start and end at 0. All right, so things we learned during this example problem. 1, distributed loads have to go back to being distributed after you solve for the reaction forces and before you draw the shear diagram. Next, we looked at how to do some complicated area under the curve, right? When you have a triangle and a rectangle combined. And then the final takeaway from this is if you have a linear, like straight line, that's not just horizontal, right? A linear shape on your shear diagram that corresponds to a parabola for your moment diagram, right? And that is it for example problem number 2.